On the exam walkthrough, we're going to be doing 2024 Jan, question number 3 and question number 19. So question number 3 says a proton is traveling at a speed v and has a uniform magnetic field. The magnetic flux density is 45 millitesla as shown, and then they've given us the force that's exerted on the proton, and they say which of the following is the expressions that gives the velocity. So we're going to have F is equals to B VQ sine theta, where sine theta is the angle between the velocity of the charged particle and the magnetic field. In this case, that would be 90. So sine theta would just be equals to 1. So we'll have F is equals to B VQ, V is equals to F over BQ. So gonna plug those in there. 45 times 10 to the raised power of minus 3 times 1.6 times 10 to the raised power of minus 19. That's going to be C. 19 says auroras occur above the Earth's poles when charged particles collide with gases in the upper atmosphere. These collisions produce tiny flashes that fill the sky with light as shown. Okay, collisions between electrons and atoms, oxygen atoms, cause the emission of green light. Calculate the velocity of electrons that would cause green light of wavelength 516 nanometers to be emitted from an oxygen atom. So if an electron and it's moving and it collides with an oxygen atom and transfers energy, and then from the oxygen atom we get the photon of green light being emitted. Okay, so what the electron transfers is the kinetic energy, right? Its kinetic energy is transferred and the electron does work, right? Collides with the oxygen atom, and then we have the green light being emitted out. Okay, and the reason for that is that, is that when this electron collides with the oxygen atom, the electron inside the oxygen atom is going to be excited and then de-excited, so we're going to have that green light being emitted. Basically, the kinetic energy of that electron goes here, and then green light comes out because this electron here is going to be excited and then de-excited. Okay, so basically this kinetic energy and this energy is going to be the same thing basically. So we're going to have the Ke of this electron, is equals to the energy of photon, which has a wavelength of 560 nanometer. So we can say half mv square is equals to hf, and we know f is equals to c over lambda. So we're gonna have half mv square is equals to hc over lambda. I'm gonna make v the subject here, so v is equals to 2hc over m lambda and square root. Plug in the values and let's get the answer. So I've plugged in the 2, then Planck's constant, speed of light. This is going to be the mass of the electron, and then the wavelength, change the nanometer to meter, and we're going to get the answer as 8.83 times 10 to the raised power of 5 meter per second. Okay, I think that's what we have to find out. So that's going to be the answer. Okay, last part of this question says radio waves are also produced during an aurora. Electrons moving in a circular path in the atmosphere emit radio waves. The frequency of the emitted radio wave is the same as the frequency of the rotation of the electron. An electron with a speed of 1650 km per second is moving perpendicular to a magnetic field with a magnetic flux density of 48 microtesla. The radio station is broadcasting at a wavelength of 220 meters. Deduce whether the radiation emitted by the electron will interfere with the signal from the radio station. Let me just remove all of this now. Okay, it's a bit of a complicated question, and you need to think a little bit for this. So I'm going to break down this question. So we got the electron, it's moving in a circle. Now the frequency at which the electron is moving in the circle is going to be equaling to the frequency of the wave this electron emits. So as this electron is moving in the circle, it's going to emit a wave. Okay, and then we have a radio station, and that radio station also has a wave. Now you studied in Unit 2 if the waves, they have similar wavelength and they're kind of similar to each other, they're going to interfere and superpose. So that's what would happen. So we know the wavelength here is going to be 220 meters. The question tells the wavelength of the wave that comes from the radio station is this much. Now we have to find the lambda value of this wave over here that's coming from the electron that's moving in the circles. Okay, so that's what we need to find out. Okay, so let's do this. So we need to find the lambda value. Now, first of all, let's look at this circle. So the electron is moving in the circle. So the centripetal force is equals to the magnetic force, because electron is moving in circle because of the magnetic field. So what I can do now is I can write mv squared over r is equals to bvq sine 90, because the electron is moving perpendicular to the magnetic field. So this cancels out. The v and the 2 here gets removed. So we're going to have mv over r is equals to bq. I'm sure you're familiar with this formula. R is equals to mv over bq. So you can find the radius, and actually that's what the question tells us as well. So I'm just doing what the question tells me. So that's going to be 9.11 times 10 to the raised power of minus 31 times 1650. It's in kilometer per second, so I'm going to change that into meters. The magnetic field is 48 times 10 to the raised power of minus 6 times 1.6 times 10 to the raised power of minus 19. That's going to give me 0.195 meters as the radius. So that's going to be the radius r. Okay, now what we can do is we can use another formula. Now before I go on to solve this question, what I'm going to be doing is I'm going to be using this formula. And I know omega is equal to 2 pi by t. And 1 over t is equal to the frequency. So we can do that. And once I get that frequency, I know that the frequency at which this electron moves is going to be the frequency of the wave that's released. And remember, it's a radio wave, which is an electromagnetic wave. So that wave is traveling at the speed of light. So I have that speed of light, I have the frequency, and then I can calculate the wavelength that I'm looking for. Okay, so I'm going to write here V is equals to R 2 pi F. So omega is equals to 2 pi 1 over t, and I'm writing that as the frequency. Okay, so let's find the frequency now. We have all the values. 1650 times 10 to the raised power of 3 divided by 0.1957 times 2 pi. That's going to give me 1.34 times 10 to the raised power of 6 hertz. Okay, now let's make this less complicated, and let me just erase some stuff here. Okay, so we have tidied things up. So we've got the frequency now as well, which is 1.34 times 10 to the raised power of 6 hertz. Let's find the lambda value, which would be 3 times 10 to the raised power of 8 over 1.34 times 10 to the raised power of 6. That's going to give me 223.6 meters. So you can say that's going to be 224 meters. Okay. So we've got this wave over here coming from the movement of electron, 224 meters. This wave coming from the radio station, 220 meters. The wavelengths are very similar. So your conclusion will be yes, wave from the electron will interfere with the signal from the radio station.